What we'll see next is a specific example, but a useful one, of continuity. Okay, so suppose we take X and D is a metric space, and now if A is a subset, and specific example which is important in this is example if X is, say, little a, oh, not X, but A is little a. Is a point. Okay, recall that we define distance of a x as being the infimum of little a in a. Oh, perhaps it's easier to write it this way: distance between x and a for all little a in a. So it's the distance to the nearest point. If a was closed, this is positive outside A itself. It's always 0 for points in A. In general, it's 0 in points in the closure of A. Okay, I think we have not proved that, but that follows from more or less the same arguments as we will see right here. So what we show is the following proposition. So this is a function of x. So distance of A with something from x to R is continuous. This complements our way of combining functions from R. And we'll see in a metric space, this is particularly important in characterizing continuity itself. Okay, so distance from A to this is a continuous function. Let's see what's the idea of the proof. Here is A, here is X. Okay, and we want to know what is the, and we have the nearest point A. What we want to claim is that if I take points close enough to X, then their distance from capital A is not very different. Well, it's not much bigger. That's because little a is only a distance between this plus this away. But it's also not much smaller, because if I have a point, it may have a different infemal point, but then this distance is not very different. I mean, then we can deduce, if this distance was very short, we can deduce that the original distance to this new point A prime is very short, which will give a contradiction to A being the nearest point. Okay, though there's no need to arrange this argument by contradiction. Concretely, we will use our criteria involving basis again. Okay, so fix a point x. Let's say x0 in x. Okay, and epsilon greater than 0. And we will show. So we find V, a neighborhood. W of x0 such that the distance between A and x minus distance between A and x0 is less than epsilon for all x in W. Okay. Actually, you could take W, because this is the distance function we are taking. You could take W to be the ball of radius epsilon itself. We'll be a little lazier and we'll take a ball of radius epsilon by 2. Okay, so let W be ball around A. Well, not A, but around x of epsilon by 2. Okay, and let call it something. We don't need to give it a name again. So let W be the ball of radius epsilon by 2. We claim this distance holds. Okay, we claim this holds. Okay, so by definition of distance between A and x0, so there exists some point A in A such that the distance between A and, not A, that was redundant, oops. Such that if I look at the distance between little a and x0, I wrote it symmetrically the other way last time. Well, this distance has to be, of course, greater than or equal to the distance between a and x0, because that was an infimum. But this is less than distance between ax0 plus epsilon by 2. Okay. So by definition of infimum, while we cannot find an a which realizes it in general, we can find a point as close as we want to that. Okay, so we took a ball of radius epsilon by 2 to not bother with refining this argument, which you can as well by taking arbitrary epsilon. And now we claim, now suppose distance between x0 is less than epsilon by 2. Well, then we know that the distance between a and x, we can get an upper bound of this straight away. This is less than or equal to distance between our chosen point. Our chosen point was a and x. This in turn is less than the distance between little a and less than or equal to x plus distance between x0, which is less than, we know two things, distance between ax0 plus epsilon by 2. That's what we know about the, I'm sorry, the whole point of this was to put an x0 here. Distance between a and x is distance between ax0 plus distance between xx0. I've used triangle inequality and symmetry here. I could have written it the other way around. This is less than or equal to distance between ax0 plus epsilon by 2 plus epsilon by 2. Okay, which is distance between ax0 plus epsilon. So what we know is that the distance between a and x is less than, so that is distance between a and x is strictly less than distance between ax0 plus epsilon. Okay, so we have got an inequality the other way. So conversely, so there exists a prime in a by definition of infimum such that distance between x prime, I was just called that, well, so that was called just x, not x prime. So distance between x, so maybe I'll just call this b, since that's not prime. Distance between x and b is, need not realize the infimum, but it's less than the infimum, which was distance between ax plus epsilon by 2. Okay. So what does this, so there exists some point which is within this distance. Therefore, we can do the same trick the other way. Now the distance between a and x0, okay, is less than or equal to the distance between the point b and x0. And now the same trick works. So this is less than the distance between b and x, which we controlled, or x and b, which is above, which is this guy, plus distance between x and x0. Okay. Fine. So from this we get the bound that, so from this we get the bound that, so this distance is bounded. And so we get, with the role of the x and x0 reversed, the bound distance between ax plus epsilon by 2, that we had a hypothesis, and this distance is at most epsilon by 2. Okay, so that is equal to the distance between ax plus epsilon. So that is the distance between ax is greater than or equal to distance between ax0 plus epsilon. So we have one inequality here and another inequality here, and these two will together tell you that you have a point. If you have a so if we look at the quantity distance between, I'm sorry, I didn't mean this one. That inequality is correct, but the inequality we proved is this one. that between them they tell you distance of ax is within plus minus epsilon of distance ax0, that is the difference between these two is less than epsilon, that is this distance rise in the ball, which is as required. Okay, so this is the continuity of distances. You can think of it as an exercise that if I took any point x here, I'm taking a different x, and I took anything within radius epsilon, anything with distance less than epsilon from this, the difference between the distances to a of these 2 points is at most epsilon. Okay, it is simply that we don't choose a in advance, but choose a adapted to the distance between these 2 points. We have done fairly similar things before. Okay, so this was an example. We can see that distances are continuous. We will next see that in many cases the correct way to define topology is in terms of what functions are continuous. And this was done as a way to provide an example for that. Okay, we have another example which does not involve metrics, which is also important, and it's part of a very general idea that you want to have what are called universal properties.